Today our speaker is Dhruv Rohatgi from MIT. Dhruv is a final year PhD student from MIT ECS, devised by Ankur Moitra. His research focuses on how to fit different blocks of fundamental blocks in machine learning together to solve more complex problems, especially those problems involving making sequence of decisions. His research is supported by American Presidential Fellowship and NDSEG Fellowship. So let's welcome Dhruv.
Thank you all for coming. So machine learning has had some incredible breakthroughs over the last few decades. As we all know, we've achieved human or even superhuman performance at problems ranging from image classification to playing strategic games to generating natural images and natural text. We have AI agents that can produce working software, and I'm told that AI can even now file my taxes for me. But there's a lot that AI still cannot do. We still don't have the ability to put AI agents out in the real world and operate in complex environments for extended periods of time. We still don't have the ability to use AI to generate and test interesting new scientific hypotheses. And we still don't have the ability to use AI to help us solve unsolved major math problems. So on the road from here to there, the dominant paradigm in machine learning as a field has been to try to increase the amount of data and the amount of computation and the amount of trial and error that we throw at these problems. And we've made a lot of successes using this idea of scaling up, but what nobody really understands is how far this paradigm can go, and if there are cheaper ways or more reliable ways of achieving the same results. In other words, what's missing are the sorts of guiding principles in machine learning that could help us understand, one, what we can do with current machine learning paradigms, and two, where we might need new paradigms, some way of sort of finding the needles in the haystack that are good algorithms for machine learning. So this is the case for why we need a theory of machine learning. Now, when I say a theory of machine learning, maybe what you are thinking of is this long-standing open problem of trying to prove that deep learning works under some realistic assumptions. And you can think of this as sort of the machine learning analog of what in physics people call trying to find the theory of everything. Somehow this is the goal in physics of trying to find some theory that explains everything about the universe. So this is a hard problem in physics, and this is a hard problem in machine learning. In machine learning, what stymies this agenda of trying to prove that deep learning works is this issue that, unlike our favorite algorithms from Computer Science 101, deep learning only works on natural data. It does not work on worst-case data. And thus far, we seem to have no way of mathematically formalizing what natural means, and we seem very far from this. The goal of my talk is to argue that we can still do useful theory without necessarily having to answer these questions and without having to develop this theory of everything for machine learning. So my perspective on how we can accomplish this, how we can develop a useful theory, is by taking a modular approach to theory building. In machine learning practice, we can observe that often the more recent successes in machine learning have built on earlier successes in some fundamental ways. For example, if you want to train a language model to generate natural text, the canonical way of doing that currently is by autoregressively generating text, by training your model to predict the next token that follows some sequence of text. And so this is a supervised learning problem that is a core building block in how generative models are trained today. So my perspective is to apply this phenomenon to theory as well. We can develop theoretical abstractions for the sorts of problems that are easy in machine learning, or easier, and try to use these as building blocks when we design algorithms for the machine learning problems that remain challenging. So if we assume that we can solve supervised learning, what else can we do? Or if we assume that I have a generative model for some task, what can I do with that generative model? These are the sorts of problems that I want to study. And in some sense, this is a very old idea, this idea of abstracting away some parts of the problem. Half of computer science is about designing algorithms. And when we design algorithms, we are abstracting away things like what programming language we wrote these algorithms, or we're going to implement these algorithms in. And when we code in programming languages, we're implicitly abstracting away things like what's the computer architecture. And you can go down this pyramid as far down as you like until we get to these details about the universe that nobody really understands. But when we design algorithms, we don't have to think about these details because we have these higher level abstractions that let us sort of sweep them under the rug. And this is my idea of what we want to do for a machine learning theory as well. We want to design a modular theory for machine learning by coming up with appropriate abstractions. What makes this easier said than done is the question of what are the right abstractions in machine learning, or at least what are useful abstractions. So to give an illustrative example, let's say that I want to use machine learning to solve the Riemann hypothesis, some very challenging math problem, nobody knows how to do it. Let's suppose that we have some machine learning model that has the ability to judge small snippets of mathematics. It can look at some lemma, and it can say, is this lemma progress towards solving the Riemann hypothesis? And it will say maybe yes, maybe no. Now, even if this is a very powerful mathematical model, it's not going to be a perfect model, because there will always be some mathematics that this model has not been trained on. It does not know. It's always going to make some mistakes somewhere, some of the time. So is it perfect? No. So a useful abstraction needs to be able to come to terms with this. We need to be able to conceptualize the sorts of imperfections that might be in this machine learning model if we are to design an algorithm that can use this machine learning model to solve the Riemann hypothesis. And then once we have an abstraction for an imperfect judge, then we can try to design algorithms that can cope with these imperfections. And I want to emphasize that this is not a specific issue with the particular example of mathematical reasoning. This is a general phenomenon that arises whenever you have a machine learning model that you want to use to solve some more complex problem. It's going to be imperfect, so our algorithms should reflect that fact. And in the first part of this talk, I will actually give some concrete examples of these questions and give some concrete answers to these questions. More generally, what I will build in this talk is a theory for long horizon reasoning. So here we're motivated by these grand challenges I mentioned before, where one of the common factors is that to solve these challenges, we will need algorithms that can reliably make long sequences of decisions or can reliably produce long chains of reasoning. The trouble with long horizon reasoning, what seems challenging, is that there's this folklore belief that long horizons of decision-making have a tendency to amplify learning errors. So you ask your machine learning model to make one decision, and it has some small chance of failure. But then you ask it to make a second decision on the basis of the first decision, and then a third decision, and so on and so forth. And if every decision has some small chance of failure, then you might heuristically believe that the chance that every single decision was correct might decay exponentially in the number of decisions that you had to make. Obviously, this is just a heuristic, but this general phenomenon has been observed empirically and sometimes even theoretically throughout machine learning, throughout subfields of machine learning. And it remains largely unclear which, if any, existing machine learning methods mitigate this issue and at what cost. For example, if you ask some frontier language model in your browser to solve some math problem, not even the Riemann hypothesis, just some proof-based math problem, as often as not, it will make a mistake somewhere in the proof. And this will break the entire proof. And anecdotally, as you ask for longer and longer, more complex proofs, the chance that you have some mistake becomes higher and higher. So this is maybe one manifestation of this issue. In this talk, what I will show is that the modular perspective to theory building can lead us towards new algorithmic principles for trying to mitigate this issue. And for the rest of this talk, I will refer to this issue of compounding errors as the so-called curse of horizon. So more specifically, in the first part of this talk, I will discuss a problem called guided generation. I have a language model, and I want to guide its progress using some sort of estimator of how much progress we're making. The key abstraction here will be some notion of a progress estimator, some machine learning model that can judge how much progress we're making. In the second part of the talk, I will look at the problem of fine-tuning language models. So now the language model is not just a black box. We want to open it up a little bit. We want to make it slightly better at imitating long demonstrations from some expert. So here we want to achieve long horizon reasoning by teaching the language model using some expert data. And in the third part of the talk, time permitting, I'll briefly discuss reinforcement learning with language models, where we want to improve our language model's ability to solve long horizon tasks by interaction with some evaluator who provides rewards. And in the second and third parts of this talk, as in the first part, one of the key abstractions we'll have to think about is a pre-trained language model. So if I give you a pre-trained language model, what can we do with this? So without further ado, let's get started with the first part. The background here is that I have a language model, and I want to use this paradigm called inference time computation to solve long horizon reasoning. What is inference time computation? Well, a language model, as it's commonly implemented today, is basically an architecture plus an algorithm. The architecture is based on transformers, and it just takes a sequence of text and it predicts a distribution over the next token. The algorithm is called autoregressive sampling. It's the standard way of using this architecture. You generate tokens one by one, you condition on them when you generate the next token. The idea behind inference time computation is that let's just use a different algorithm. Maybe there's a better algorithm besides autoregressive sampling. And the grand hope here is that by throwing more computation at inference time, by using a more expensive algorithm, we can maybe improve the reasoning abilities of our language model, of our base architecture. As one concrete example of this hope, some people have suggested that if you ask your language model to just think for longer, it becomes smarter. And there's some evidence that maybe this works, at least to some extent. But there's also some countervailing evidence that if you ask your language model to think for too long, then the errors start to compound. So somehow the key question in this field of inference time computation is, can we scale up computation without suffering this, without suffering compounding errors? And can we get to this long horizon reasoning holy grail this way? So that's the background. The hope that's emerged in recent years has been to try to mitigate the errors that the language model would itself otherwise make by some form of step-by-step supervision. And formally, I'll introduce to you something called a process verifier, which is some way of trying to provide this supervision. The issue that we will have to contend with is that, of course, this supervision is itself going to be imperfect, that process verifiers are themselves imperfect, and we never have exact measures of how much progress we're making. And what's worse is that you can show that if you were to use the process verifier in some naive way, then any imperfections in this process verifier will have a tendency to compound, even in very simple tasks. So now we have this language model. The language model is making errors every time we generate a token with some probability. We have this process verifier that's making errors every time we judge how much progress we're making. So we have two imperfect models that keep on making errors. And we might wonder if we're somehow fundamentally doomed to these errors compounding, or if there's anything better that we can do. What we show is that in maybe surprising generality, we can actually mitigate some of these imperfections. We can mitigate some imperfections in our supervision by allowing the chain of reasoning produced by the language model to not just go forwards, but also to go backwards. So some form of backtracking will mitigate errors. This is not just a heuristic. We'll show that we can get provable guarantees for this backtracking-based method by connections with the classical and modern literature on approximate sampling. And this will give us some insight into a class of imperfections that can be tamed. So a class of imperfect supervisors that can let us mitigate errors and avoid this curse of horizon. Yes?
Is the process verifier's error two-sided or just one-sided?
I will give a formal definition later, and maybe that will answer the question. So first I need to tell you what process verifiers are. And before I do that, let me tell you about something slightly simpler, which is an outcome verifier. So an outcome verifier is some model that can provide numerical scores for complete responses from your language model. Like think of a complete proof. It can assess if this is a good proof or a bad proof. If you have an outcome verifier, what can you do? One thing you can do is you can generate not just one response from your language model, but a bunch of responses. And just pick the best one. You use your verifier to identify the one which has the highest score. This is called the best of n pipeline. It's super common in practice these days. It's pretty useful. So you can use best of n to saturate some sorts of mathematics benchmarks using a weaker model than you might otherwise have been able to do. But can you use best of n to solve the Riemann hypothesis? Maybe not. The issue is that if your language model is exponentially unlikely to solve some problem, then best of n requires an exponential number of generations before you can hope to find a correct generation. This is the issue that process verifiers hope to mitigate in some way. A process verifier is a model that can score not just complete responses, but also partial responses. It can tell you how much progress you're making. And if you have a process verifier, you can do all sorts of more interesting things. You can generate a single token from your language model and ask the process verifier for some score. And if it's bad, you could try a different token. If it's good, you could build on that and try 2 tokens, and so forth. And then you finally output some response. So this is a very flexible paradigm. There's a lot we can imagine doing with this. And there's some formal sense in which this paradigm is very powerful. In particular, if you have something called a perfect process verifier, which I will define formally a little bit later, you can actually solve NP-hard problems in linear time. You can find a solution to a given SAT formula in linear time in the number of clauses and variables. How do you do this? The intuition is pretty simple. You just guess the value of the first variable. You say, is x1 equals 0 valid? And your process verifier will tell you if x1 equals 0 is progress towards a satisfying assignment or not. And if it is progress, then you're done with that. You just try the second variable. And if the second variable is bad, then you know that you have to try x2 equals 1. So at every step, you get some bit of information, and you can make progress.
So it's basically a reduction from optimization oracle to a decision oracle?
Yes. So this seems great. Like, we can solve all of our problems with perfect process verifiers, or at least we can solve some pretty challenging problems. What's the catch? The catch is, of course, that we do not have perfect process verifiers in practice. So anything that we could hope to learn or to heuristically generate is going to be imperfect. So in practice, there are ways of estimating process verifiers from data. These are machine learning models, so they will be imperfect. And so if we want to design algorithms that can use process verifiers, we need to be able to understand how we can use imperfect process verifiers. And here I want to point out that while there are a variety of heuristics in the literature for generation with process verifiers, and some of them are even implicitly trying to cope with this problem of imperfections, nobody has made this problem precise. What is the problem we're trying to solve? When might we hope to solve it? And that's what we're going to do. So this brings us to our problem formulation, where I will get more technical. We will formalize the problem, and we will show that with naive usage of the process verifier, imperfections do compound. The problem is a sampling problem. I give you a language model. We'll call it pi. It takes a prompt, and it produces a distribution over responses. We'll assume that complete responses have some fixed length capital H, which we'll call the horizon. We also have some reward function R. It takes a prompt and it takes a complete response. And it produces a non-negative real number. And the goal of the thing we want to solve is sample from the distribution pi star, which given some prompt x, has density proportional to pi times the reward. Why is this a problem we care about? Well, suppose you think of the reward as a binary function. It's measuring correctness of your response for some given problem. So it's 0 or 1. Then sampling from pi star is exactly a constrained sampling problem. You want to constrain on the reward being 1. So maybe you want to generate a proof from your language model, and you want to be sure that it's actually a correct proof to the Riemann hypothesis, and not some like, I don't know, quack attempt. So if your base language model is very bad at producing higher reward responses, this might be a very hard problem. To try to make this easier, we'll assume we have a process verifier that can control our errors. And we will formalize the process verifier as something called an approximate value function. What do I mean by this? The true value function v star for some partial sequence of tokens, so think of this as some partial proof, is going to be a conditional expectation. It's the expected reward that you would get for a complete response conditioned on your partial response if you were to complete it using your language model. So it's saying that if you have high value, then your partial sequence of tokens is likely to lead you towards high reward. If your sequence of tokens has low value, then you're very likely to go off track and get low reward. So that's the meaning of a value function. Because in practice, value functions are not going to be perfect, they're going to be estimated from data, it's not reasonable to assume that we have access to V star. This is just too intractable of an object. So instead we assume we have access to this approximation, which we'll call V hat. The exception is for complete responses. For any complete response, the value is equal to the reward. So we're happy to assume that we have the true value for a complete response. But for any partial response, computing the value is very hard. We only have some approximation. So that's the setup. What was known about this problem? Prior to our work, all that was known was that if V hat is equal to V star, so if we did have the true value function, then we would be happy. Then we could sample from pi star in linear time by an algorithm that we'll call token level reweighting. The algorithm is simple. It looks a lot like autoregressive sampling. At every step, you generate a token conditioned on the previous tokens. The only difference from autoregressive sampling is you reweight each conditional distribution by your value function. And you can show that if the value function is equal to V star, if V hat equals V star, then you're sampling from the right distribution. The catch is that this algorithm is not robust. So essentially any errors in the approximate value function will be compounded by this token level reweighting algorithm. Intuitively, because at every step you're making some irrevocable choice of which token you want to generate, and you never go back and fix your mistakes. And this is the source of the plot that I showed earlier. We have some simple task where we can vary the horizon, the number of tokens we're trying to generate. And we can measure the KL divergence between pi star and the distribution that we're generating using token level reweighting, using some approximate value function. And what we see is that the error indeed grows as the horizon gets bigger. So we are suffering from error compounding. And so this motivates the question, can we get better algorithms that avoid error compounding by doing something more clever than token level reweighting? And this brings us to our work, where we show that in fact we can. So the approach that we will take is a stochastic backtracking approach. You can think of our algorithm, which we'll call value-guided backtracking, or VGB, as performing a random walk on the tree of all possible partial generations from your language model. So this is all possible sequences of length up to capital H. It's a random walk, so you've started some node, which is some sequence of tokens, and then you have some probabilities. You have some probability of going down the tree, which corresponds to appending a new token. And you have some probability of going up the tree, which corresponds to erasing the most recent token you generated. And you decide based on these probabilities, maybe you go down the tree in the first step, maybe you go up the tree in the second step. What are these probabilities? The probability of going down the tree is actually going to be the same as in token level reweighting, up to some constant of proportionality. It's the conditional probability under the base language model pi, multiplied by the approximate value function. It's the same thing. The difference is that we have this probability of going back up the tree. This backtracking probability, which turns out you want it to be proportional to the approximate value of the current node. And you can think of this as essentially a one-line correction to the token level reweighting algorithm. You just sometimes decide to go back the tree, like to go back up the tree and delete a token, instead of always just generating tokens. Where does this come from? It turns out that it's actually a new application of an old technique from the 1980s by Sinclair and Jerome. They were working on something called sampling to counting reductions for the SAT problem. And they had the same idea of using a random walk to mitigate error compounding. I'm not going to say more about that in this talk, but if you're interested, I can talk more about it later. I'll also mention that backtracking heuristics have been tried before in practice for these sorts of problems. And this algorithm can be thought of as a principled way of backtracking. So it's explaining what is the way that we should be doing backtracking. What do I mean by saying that it's principled? Well, here's the theoretical guarantee, informally. It says that if for any partial response, or sort of on average over partial responses, the approximate value and the true value are multiplicatively close, then our algorithm samples from some distribution that approximates pi star, the distribution we want to sample from. And our algorithm does it in polynomial time in the number of tokens that we're trying to generate. There are some technical details that I'm sweeping under the rug about what exactly it means to approximate pi star, and what exactly I mean by this algorithm. I've only told you a random walk. But I'm going to assert that these are not conceptually important, and I could talk more about them afterwards.
One quick question about
Yes.
just the other quantifiers here. When you say that it's on average with respect to W star, this is for every state on average, or also on average over the states?
So this is you condition on the prompt.
Yeah,
and then
that's fine.
You fix some length little h, and you look at the expectation under pi star of all like partial responses. So it's not
Okay, so it's
every
both
state.
over the partial response and the action. The expectation.
Yes, the expectation is over the partial response.
I see.
Yes.
Is there mixing? I mean, the paper you referenced, this is a Markov process.
This is a Markov problem. We'll talk about mixing.
It feels like the mixing time would be large.
It turns out under this assumption it's not large.
It proves it's not.
That's the point.
Oh, that's the.
So the takeaways are one, that this algorithm avoids error compounding in some provable sense. Under the same assumption, token level reweighting can sample from a distribution that's essentially arbitrarily far from pi star. And we're avoiding that. And the other thing I want to point out is that we're actually using the process verifier in a fundamental way. So you cannot get this guarantee by just using your outcome verifier and running something like best of n or rejection sampling at the trajectory level. You have to fundamentally use the process verifier to get this exponential speedup.
Are you gonna talk about
I will
that
come
in-
back to
to this can't use best of n? You're gonna come back to can't use best of n? So I'm curious, when you say can't use best of n, if you do some kind of like you maintain a frontier in the tree and do best of n on that somehow, is that?
I just mean that if you don't have a process verifier, you only have an outcome
Oh, if you
verifier.
only have that in the
Yes.
process verifier.
Yes, then you cannot get this
Oh,
sort of
okay,
guarantee.
yeah,
Yes. So that was a theoretical statement. So what actually happens with value functions that you might hope to get in practice? One way of training a value function in practice is by some sort of regression. You draw a bunch of responses, you regress the rewards onto partial responses. So we can run some simple task using this approximate value function that we trained this way, and we can measure KL divergence of our approach versus token level weighting to the true distribution pi star. And we get the plots that I showed earlier, where our algorithm flattens the curve, so it mitigates error as the horizon grows. It doesn't avoid it completely, but maybe we should not expect that because the theoretical assumptions do not necessarily hold in this setting. So this shows that there are some empirical benefits, even though the theory may not hold here. This is a pretty simple setting where pi is the base language model is actually very simple. We have a slightly more sophisticated experiment, which is constrained language generation, where you have a language model, you want it to generate some text that does not use some particular letter. So this is a constraint. And small language models are actually very, very bad at this task. You can use token level reweighting. It will be better. It will avoid the letter E, but it will do this at the cost of coherence. It will just misspell words to avoid this letter. So our algorithm improves coherence in some sense according to some language model judge. And it's also orders of magnitude faster than best of n. Than just generating text until you avoid the letter E by chance. So, yes.
So here hamburger is not one token. Your token is just a character.
I'm not sure exactly what the tokens are here. I would guess that there's like maybe ham is one token, burg is one token or something.
Okay.
Or it's possible that this misspelled word is also in the vocabulary. I'm not sure.
I see. So this is probably a small model trained by yourself, not like off the
No,
shelf.
this is Quen 0.5b.
No, so hamburger is a token, but probably that's like multiple tokens. Right?
With the misspelling.
The misspelled word is probably 2, 3, 4 tokens.
I would guess so, but I'm not actually sure. Yeah. But yeah, this is Quen 0.5b. So now I want to turn back to the theorem and give some flavor of why this works. So how are we getting these speedups? And in particular, how is this sort of one-line correction to token level reweighting getting us these improvements? To answer this question, I need to discuss the stationary distributions of random walks. So I'll take a brief technical interlude here. A random walk is defined by some states and some probabilities. You start some state, and based on the probabilities, you decide what's the next state. That's one step. You do this some number of times. The stationary distribution of a random walk is just essentially the distribution of where you expect to be after you run the random walk for long enough. So some asymptotic notion of where you expect to be in the state space. So in general, stationary distributions might be very complicated to describe for generic random walks. And for some technical reasons, they may not always actually even exist. However, there's an important class of random walks for which stationary distributions do always exist and have a very clean description. These are undirected random walk. So an undirected random walk on some state space is defined by some weights on the edges. The probability of transitioning from some state I to some state j is proportional to the weight on the edge between I and j. And you can show that the stationary distribution of any undirected random walk is proportional to the weighted degrees of the states. So for state I, it's proportional to the sum of the weights on the edges adjacent to state I. The reason this is relevant for us is because our random walk is actually equivalent to an undirected random walk on this tree. So the weight on any edge turns out to be proportional to pi times v hat. And because of this fact about undirected random walks, we have a clean description for the stationary distribution on this tree. It's just the sum of the weights on all the edges adjacent to the node that we care about. Now, what we ultimately care about is not sampling partial responses. We don't care about partial proofs for our Riemann hypothesis. We care about complete proofs. And these correspond to the leaves of the tree. So we want to sample from the distribution pi star, which is a distribution on the leaves of the tree. Now, any leaf node only has one edge adjacent to it. So actually the stationary distribution simplifies even further. It's just for any leaf node, the stationary distribution is proportional to the weight of the edge adjacent to that leaf node. So that's just a single weight, pi times v hat, for that leaf node. And now we can recall that for any leaf node, for any complete response, we know the value of that response. It's just the reward. So the probability that our random walk ends up at some leaf node will be proportional to pi times v hat, which is pi times the reward, which is exactly the distribution that we were hoping to sample from. So this is good news in some sense. It tells us that if we were to run the random walk for infinitely long, or if we were to run it to stationarity, then conditioned on reaching a leaf node, we are sampling from the correct distribution from pi star. So this is some principled explanation that as we run the random walk longer and longer, we are converging to the right distribution. Yes?
So I'm a bit confused here. So in the stationary distribution, you can also go from the leaf node back to the like just before. And when you say condition on reaching the leaf node, do you mean that like the first time you hit the leaf node?
So for the theoretical guarantee, what you do is you run for some fixed large number of steps. If you're not at a leaf node at that step, then you have to repeat.
Oh.
When you implement it practically, you can do some like simpler heuristics. So this is some progress. We've shown that the stationary distribution is pi star. This doesn't prove the theorem because we do not want to run a random walk for infinitely long. We want to run it for some bounded amount of time. So now I have to tell you a little bit about why the algorithm mixes to stationarity quickly. I'm only going to give some flavor of the issues here. I'm not going to give sort of the full proof. And the issue that we face here is that you actually have to go beyond classical Markov chain theory to prove this. So classical Markov chain theory says that no matter which state you start in your random walk, if you run your random walk for some number of steps, some not too large number of steps, you mix to stationarity. You forget your initialization. And you prove this essentially by arguing there's no bottlenecks anywhere in the graph, in the random walk. So this would suffice for what we were trying to prove. If v hat and v star were close everywhere, at every node, v hat and v star were close, because we'd have some uniform control on the random walk. But this is not a reasonable assumption for machine learning applications where v hat is some learned model, and it can make errors where it has poor training data. So our challenge we have to face is that bad initializations definitely exist. There could be some small part of the state space where we had no training data for a value function. And so if we start a random walk in that part of the state space, we sort of have no guarantees of what happens. There could be a bottleneck, and we could just never mix to stationarity. So the only hope for us is essentially that there might be a good initialization. Our hope is that if you start with a good initialization for your random walk, then you do mix to something that's close to pi star. In other words, what we need is an initialization-aware theory of Markov chains, where depending on where you start, affects where you end up. We get this by drawing on some recent work on locally stationary distributions for Markov chains. A locally stationary distribution can be thought of as the sampling analog of critical points in non-convex optimization. So when you run gradient descent on a non-convex function, you always end up at some approximate critical point pretty quickly, but which critical point you end up at depends on where you start. And the same thing is true here in the theory of sampling. For our purposes, what we show is that if you use the correct initialization, which is just the empty sequence of tokens, and you run your random walk to local stationarity, which happens in polynomial time, then we get the guarantee that we wanted. We have this approximate coverage of pi star, which is what we wanted to prove. And this is all I want to say about this theorem, and all I want to say about this part of the talk. So to summarize, we showed that in the setting of generation with some imperfect supervision, we can mitigate imperfections by allowing reasoning to backtrack, we can get provable guarantees, and this gives us some insight into a class of imperfections that can be tamed. And this opens the door to asking more general questions, like, here we show that approximate value functions suffice for avoiding the cursive horizon. But what else can we do beyond that? What other forms of supervision would let us avoid the cursive horizon and get long horizon reasoning using this idea of inference time computation? So that's the general agenda here. Now I want to switch gears completely, or mostly. And let's open up the black box. We have language models. We want to fine-tune them to imitate long demonstrations. And I'll briefly talk about some related work on imitation in the context of robot learning. So here the background is that you want to train a decision maker or a language model to perform long horizon reasoning or perform sequential decision making by imitating some expert. So it's a student learning from a teacher by example. In the context of language models, this is the paradigm of supervised fine-tuning, which is one key step in language model training. You collect a bunch of training data from some expert. Maybe a mathematician gives you problems and solutions for math problems. And then you just update your language model to try to imitate the training data. The algorithm that's used in practice traditionally is something called next token prediction. You look at every token in your training data, and you look at the text that preceded it. And you try to update the weights of your model so that it's good at producing that particular token given that particular text. That's next token prediction. That's the dominant paradigm for supervised fine-tuning. Here's another setting where the same paradigm appears, which is in robotics with imitation learning. You collect data from a human who is showing you how to manipulate some object, and then you update your model to try to be better at imitating the human. Here the algorithm is called behavior cloning, but it's really the same idea. You look at every action taken by the human, and you look at the context in which this action was taken. And then you try to update your model to be better at producing those actions in those contexts. So we have behavior cloning in this setting, we have next token prediction in the language model setting. These work well often, but they have sort of a key limitation, which is that they tend to compound errors across long horizons. So you ask your language model or your decision maker to produce one decision or one token, but then you ask it to produce even more decisions or more tokens. And what you can observe empirically in many regimes is that the error grows with the number of tokens you make, with the number of tokens you produce, or the number of decisions that you make. So in our works, what we try to understand is when and how can we avoid this? When can we avoid this instantiation of the cursive horizon? So one existing fix in the robotics literature is something called interaction. Instead of just generating data from your expert and then training on it, you can put the expert inside the training loop. You can generate data, train on it, generate new data in particular settings, and then train on that new data, and so forth. And this has some benefits empirically. But there's two issues. First, in some settings, interaction is not available, like in the language modeling setting. It's not that reasonable. And second, it's not always clear, it doesn't always work, and it's not clear when it works. So this raises two questions about this cursive horizon. First, if we do not have interaction, what can we do? Can we design algorithms that are better than next token prediction and behavior cloning that mitigate error compounding in some way? And second, in the interactive setting, what's happening? So in particular, as a starting point, can we understand when the standard methods for interactive imitation learning avoid error compounding and when do they suffer from error compounding? And I'll give one brief slide on each of these. So without interaction, this is a setting motivated by language models and supervised fine-tuning, where you don't want to call up your mathematician and say, like, what should I do in this particular step of my proof, like halfway through your training run. So here we don't have interaction. As a theoretical abstraction, we're going to consider this version of fine-tuning where we think of a language model as being frozen except for the last layer. And we think of fine-tuning as essentially tuning the last layer of this language model. This is not how fine-tuning exactly works in practice today, but there is some empirical evidence that this is some rough approximation. And this is something people do, roughly speaking. And what can we prove in this setting? We can prove that you can actually mitigate the error compounding suffered by next token prediction with a more clever algorithm, albeit at the cost of increased computation. The idea is basically to move beyond this paradigm of token by token prediction. Instead of trying to predict each token conditioned on the past tokens, we will predict the tokens, we'll learn the distribution in chunks of size k. K is some parameter that we can tune. And to learn each chunk, we will use some ideas from classical statistics to avoid error compounding within the chunk. And we'll show that whenever k is not too large, we can implement this computationally efficiently. So this gives us a trade-off between error and computation. What about the interactive side? Here the motivation is going to come from robot learning. Yes?
Can I ask a question about, so, I mean, the runtime, you said it's whenever k is not too large, you can do it computationally efficiently, but the runtime is still exponential in k?
Yes.
And so overall, how much benefit do you get? I mean, considering you can take k to be too large, and then you still get like linear in horizon.
Yes. You're just getting you're getting like h divided by k. Yeah. And there is some. You can also prove that you cannot avoid it completely without paying computation. So in this theoretical test bed, there's a lower bound for avoiding error, like amplification entirely. But exactly where the line is, that's not so clear.
So would you expect if the error needs to be sublinear in horizon, you need to pay for more than?
I would expect that there's a lower bound, but we don't have exactly that. Yeah. So one setting where interaction is reasonable is in robot learning, where you want to learn on the basis of visual data, but you have a simulator for the environment. So learning a decision maker from visual data can be very challenging in practice. When you have a simulator, you have access to the latent states of the robot. So you have access to the joints, the positions, the velocities, and so forth. And you can learn an expert that gets to see these latent states and make decisions based on them. This turns out to be easier. What you care about is a decision maker that only gets to see the visual data. This is more practical. So you want to learn a student by using this expert to help you learn. And to get from the expert to the student, you use imitation learning. Because the expert is a machine learning model, you can query it inside the training loop. You can call it up on whatever state you want and ask the expert, what would you do? So this is a setting where interaction is reasonable. But nevertheless, this algorithm doesn't always work. And our work helps understand when this algorithm should work and when it should not work. And what we show in particular is that the stochasticity of the environment, so whether it evolves deterministically or stochastically, is a key contributor to whether this interactive imitation method suffers from error compounding or not. And then we show that in stochastic environments, you can actually mitigate errors to some extent by a sort of counterintuitive intervention of imitating a slightly worse expert. You can get a better student by imitating a worse expert, as long as it's smoother in some way. So that's all for imitation. This is sort of just a proof of concept about how to improve imitation learning in the setting of interaction, and it opens the door to asking whether there are even better methods. So we haven't fully explored what is the algorithm design space here for interactive imitation learning. Okay, so in the third part of the talk, I was going to briefly discuss reinforcement learning with language models. I'm going to skip over that in the interest of time, but I can discuss it later if anyone's interested. And instead, I'm just going to discuss how this work fits into my broader agenda. So we had these grand challenges that we wanted to solve. And the key, what we needed to solve these is we need algorithms that can learn to produce long sequences of decisions reliably. They can learn from limited data, and they can learn to interact with dynamic environments that could be very variable. So to get a handle on all these challenges, what we need is to be able to understand, one, what we can do with current machine learning paradigms, and two, where we need new paradigms. And that's the general goal of my work, to develop principles for these sorts of problems. In this talk, what I showed you is how we can use language models as a building block to try to understand when we can solve long horizon reasoning tasks. A second thrust of my work is about decision-making in dynamic environments. So motivated by settings such as robotics, you want to send out an agent to interact with some changing environment. And my work studies how we can do this using the sorts of building blocks that we have at hand, that we understand better, such as supervised learning. If I give you the ability to solve certain types of supervised learning problems, when can you solve this decision-making problem? And a third direction of my work studies what you can do with popular machine learning methods. So for the sorts of machine learning methods that are commonly implemented in settings such as distribution learning or decision-making or beyond, can we theoretically and sometimes even empirically understand in some principled way what are the benefits of these methods and what are the limitations to identify where we might need new methods. And I think all of these directions are interesting to study further. I want to point out a few other future directions that I think are particularly important and exciting. One of them is about understanding the power of diffusion models. One of them is about decision-making in the presence of partial information. And one of them is about whether we can use theory to guide us towards new paradigms for training generative models. And I'll give one slide about each of these. Diffusion models are a basic way of learning distributions. They're very commonly used throughout sciences, medicine, and robotics. But in these applications, often we do not want to sample just from a single distribution. Often we have a variety of tasks we care about, and we might want to steer the diffusion model towards these particular tasks, or constrain the model in some way. Or we might want to solve some sort of inference problem. So I give you some observation, some measurement, and I want to sample from my distribution, sort of conditioned on this measurement. So how do we do this? There's a lot of heuristics for this problem, but there's no understanding of when these work or what problems they are solving. So I want to understand, first, how do existing tools in our toolbox work? What are the benefits of methods such as backtracking or particle filtering for this problem of steering diffusion models towards some reward? Can we design new algorithms for steering with provable guarantees, perhaps by connections with classical literature on sampling? And more broadly, can we understand questions like how the problem of steering diffusion models relates to the problem of steering language models that I discussed earlier? Or what if we care about things besides just sampling from some tilted measure? What if we care about reward maximization? What if we care about diversity over generations? These are all important problems in these applications. How do we formalize these problems and develop algorithms for them? On the decision-making side, partial information is one challenge that we have to contend with in many different applications. Your decision maker is operating in some environment, but they never observe the full state of the environment that they're operating in. This is a challenge in robotics, this is a challenge in medical decision making, and many other settings where you would hope to employ a machine learning agent. But here again, the algorithmic toolkit for reinforcement learning with partial information is very limited. It sort of consists of looking at recent observations and hoping that these are enough to inform your environmental state. So I want to understand when we can get better algorithms, perhaps by reduction to problems that we understand better, such as supervised learning, or even reinforcement learning when we have full observations. One of the challenges that this requires addressing is that in reinforcement learning with partial observations, optimal policies are often very complicated to describe. So can we develop assumptions under which optimal policies are succinctly representable? Or can we even understand weaker goals that we could hope for? Can we hope to compete with sort of policies that are not optimal, but are still good enough in some sense? And finally, can we try to use powerful machine learning primitives to help us solve this problem better? So if I have something like a language model that can summarize the entire history of my observations, how should I be using this to make decisions effectively and to do reinforcement learning effectively? Finally, most of this talk was about asking the question, what can we do with current paradigms? What can we do with language models? What can we do with diffusion models? And so forth. And I want to just briefly talk about this question of where we might need new paradigms. So one dominant paradigm today is this trend towards these giant and opaque foundation models. And these have had incredible successes, but they are both expensive And they are also untrustworthy in some senses. So when they fail, we don't really understand when or why they are failing. To move beyond this, one thing we need is more controllable generative models. So we need to rethink maybe how we train generative models in conjunction with how we're going to use them at inference time, so that we can provably steer them towards desired outcomes, so that we can constrain them in our desired ways. And second, we need smaller generative models. So how should we learn smaller generative models? The key challenge here is that classical statistics is largely developed around this idea of trying to learn the distribution, or at least approximately learn the distribution. What solution concepts can we hope for, and what statistical estimators can we hope for when our generative model is not large enough to represent the entire complexity of the data that we are learning from? How do we design algorithms when we're trying to learn only part of the distribution? This is sort of a brief overview. I'm happy to talk about these afterwards too. Thanks for listening.
We have time for a few questions.
Many questions. So I'm actually curious, can you, so use, if you have an imperfect verifiers, you've talked about the use it for inference time improvements, can you use it, how do you use it for learning?
That's a good question. I guess the thing that briefly has come to my mind, but I've not actually pursued it, is you can try to use it in the reinforcement learning loop. So often you're trying to do, in reinforcement learning, you have to collect data using some sort of value. The value is not perfect. Maybe you can use similar ideas to like come up with better strategies for this piece of the RL algorithm.
And what about, so the your v hat is with respect to the same policy. What about if the v hat is with respect to some other policy? Which we either know or don't know. I mean, mostly don't know, I guess. Does that help you? They give you a v hat that's an approximate value function with respect to some unknown policy.
Yes.
Does that help you?
That's an interesting question. I mean, if it's with respect to the optimal policy, then I would guess it somehow must. Then you should be able to do some greedy thing. If it's some known policy, maybe you could try some change of measure. If it's
unknown policy, then might as well use that policy to generate, right? An unknown policy.
Yeah, I'm not sure.
I have more questions, but maybe I'll ask you later.
Okay.
Lots of questions. So in the first part of your talk, you mentioned a particular example where the rewards are binary, like you just want to, is this a correct satisfying assignment or not?
Yes.
In that case, if they were binary and your goal was just to find some correct version, then if you had an approximate value function that was multiplicatively approximate,
Yes.
then it would be sufficient to just pick any child where it's non-zero.
Yes.
Right, because you're just trying to find something. So,
Yes.
and if it says it's not allowed to say non-zero when the right answer is 0, because that would be a
Yes.
unbounded multiplicative. So, where that might fail is if it's not multiplicatively close everywhere.
Exactly.
So I'm trying to understand a little bit is, in the case where you have these 0 ones, you've got multiplicative approximation, but it's not multiplicatively close everywhere. Is there a significant advantage to kind of backtracking versus, like another approach would be to sort of randomly, just try random paths proportional to the value, and if it fails, just try it again. Do you know is that case an interesting case for your results, or is that kind of not really an interesting case for your results?
So I think it's interesting. I think the worry, which I think should show up theoretically, and I would believe also empirically, though I'm not sure, is that you go off distribution when you're doing this. Like when you're choosing sort of arbitrary things with high value, then somehow you have no idea even if you have some like average case guarantee, you don't know like what distribution you're at some deep node of the tree. So you're exploring parts of the tree that maybe you should not have been in. I think that's the worry with the sort of greedy approach.
I guess, so what was the specific assumption of, so if it didn't have to be approximately close everywhere, then it should be approximately close from most places according to what distribution did you?
Pi star.
According to pi star.
Yes.
So in other words, if you were to sample from the correct,
Yes.
okay, so that's the.
I think this might have been similar to this question, but it was on the topic of like initialization and like making sure that like didn't initialize somewhere or like travel to a part of the tree where you didn't have the training data. Can you like expound a little bit on that and how you kind of like got around that as well?
Yeah, so in some sense this is sort of a technical point in the sense that the initialization that turns out to be good is the one that you would expect. Is you start with the 0 tokens generated, and your random walk just starts from a clean slate. And the reason that this works is sort of under these assumptions that we have, sort of the bulk of the tree that you're exploring is sort of good for your random walk. There could be small like subtrees near the leaves that are bad, but if you start at the root, then you're sort of unlikely to end up in these. The bad case that the analysis has to rule out is that if you started in one of those bad subtrees, then your random walk would not necessarily mix.
And by starting with like the blank slate, you're just like guaranteed to start at least like at the root when you're at the root.
Yeah, so we just start the random walk at the root.
So, okay, sounds good. So let's thank the speaker again.